Hey everyone, and welcome. Today we are diving deep into machinability, really the science of what happens in that tiny violet moment when a tool meets metal. We're going to break it all down into a kind of masterclass, giving you the core concepts you absolutely need to know. So let's get right into it.
So let me start with a question for you. What makes something like a super alloy, these incredible materials that are super strong, lightweight, and can take a ton of heat, what makes them an absolute nightmare to machine? It turns out the very things that make them super are what make them so incredibly difficult to cut and shape. Let's find out why.
To get to the bottom of that, we've structured our breakdown around three key pillars that really define machinability. We're going to start with the material itself, then we'll look at the insane heat that gets generated during the cutting process, and finally, we'll explore the hidden damage that gets left behind.
All right, first up, the material's core identity. Long before a cutting tool even gets close to it, a material's built-in properties have already set the stage for the machining battle that's about to happen. Think about it this way. Hardness is just the material's brute strength. The harder it is, the more force it's going to take to cut. But what's just as important is its microstructure. That's the internal arrangement of its crystals. It's kind of like a building's architecture. It determines exactly how the material is going to resist being torn apart on a microscopic level.
Now, this table really brings the theory to life. Ozdemir's research confirms what you'd expect. Higher hardness means you need more force. Simple enough. But look closer. Zhao and Dalatabadi found that these tiny, super hard particles called carbides act like microscopic roadblocks. Because they're so much harder than the steel around them, they don't cut cleanly. Instead, they just resist the tool, causing this intense, localized stress that basically shreds the cutting edge and wrecks the part's surface. On the flip side, Roy's work shows that if you can get a nice, uniform microstructure through heat treatment, you end up with a much smoother, more predictable cut.
And the damage isn't just on the surface. Check this out. As Zhou's 2025 study on hardened steel shows, a worn-out cutting tool doesn't just make a rougher cut. Oh no. It fundamentally changes the material's microstructure, creating this brittle, damaged white layer right on the surface.
And by how much, you ask? A staggering 143.75% increase. This isn't just a surface scratch, people. This is a deep, brittle layer of damage that's caused by the cutting process itself. It's a direct consequence of that worn tool clashing with the material's internal structure.
Okay, let's move on to our second pillar and see how this all connects. The intense, incredible heat that's generated during the cut. Because machining isn't just a mechanical process, it's very much a thermal one too. So the crucial property here is thermal conductivity. It's all about a material's ability to get rid of heat. When you're cutting metal, you are generating insane temperatures right at the very tip of that tool. And if that heat can't escape quickly, it just gets concentrated in one tiny spot. And this slide right here perfectly illustrates what happens next. Poor thermal conductors, titanium is a classic example, they trap heat right at the cutting zone. This basically cooks the cutting tool until it fails, and it can even warp the part you're trying to make. Good conductors, on the other hand, they pull that heat away, protecting both the tool and the final product. It's a huge difference.
So if heat is the enemy, how do we fight back? Well, engineers have come up with some pretty creative solutions. These advanced cooling strategies you see here are a total game changer. From blasting the cut with liquid nitrogen to using ultrasonic vibrations, the goal is always the same. Get the heat out and get it out fast.
Let's just zoom in on cryogenic cooling for a second. It's a pretty simple idea, but it's extreme. As friction generates this firestorm of heat, a jet of super cold liquid nitrogen hits the cutting zone. The temperature just plummets, and this not only saves the tool from melting, it actually makes it harder and more effective. The result? Better tool life and a much higher quality final part. Pretty cool, right?
And that brings us to our third and final pillar, the invisible damage that's left behind long after the machine has stopped running. See, the cut itself is really just the beginning of the story.
First, let's talk about something called work hardening. The intense pressure and deformation from the cutting tool can actually make the surface layer of the material harder than the stuff underneath it. It's this vicious cycle. Each pass you make just makes the next one even harder to do.
The cutting process also leaves behind these hidden forces inside the part, and we call them residual stresses. You can't see them, but these internal tensions and compressions can have a huge impact on how that part performs and how long it lasts.
But here's the really fascinating part. Not all stress is bad. Tensile stress, which is trying to pull the material apart, is dangerous. It's like a ticking time bomb that can lead to cracks and failure down the road. But compressive stress, which squeezes the material together, can actually be a good thing. It can make the part stronger and more resistant to fatigue. So the goal of a great machining process is to minimize the bad stress and, if you can, maximize the good.
And we can see that in action right here. Zhang's study on Inconel 718 shows that an advanced cooling technique, cryogenic MQL, which is basically a super chilled, high-pressure mist of lubricant, doesn't just create a smoother surface, it also creates a much healthier state of residual stress. That means the final part won't just look better, it's actually going to perform better and last longer. So let's tie all of this together. We've looked at the material, we've looked at the heat, and we've looked at the aftermath. So what's the complete picture here? The biggest takeaway is this: machinability isn't just one thing you can measure with a single number. It's a dynamic, complex equation. It's this incredible interplay between the material's built-in properties, the thermal chaos of the cut, and the mechanical damage that's left in its wake. Truly mastering manufacturing means you have to understand and control all three of these pillars at the same time.
And that leaves us with a final thought to chew on. As our materials scientists keep pushing the boundaries to create stronger, lighter, and more durable alloys, are they also unintentionally creating materials that are nearly impossible to shape? The ongoing challenge is to make sure that our ability to actually make things keeps pace with our incredible ability to invent them.